It's wild, isn't it, how much we rely on these things we can't even see. Semiconductors.
Yeah, it's pretty mind-blowing.
I mean, our phones, cars, the internet, it all comes down to these tiny, tiny components.
hmm And the crazy thing is, a huge chunk of the most advanced ones, well, they basically come from one place.
Exactly. And that's what makes this deep dive so fascinating. We're talking about an announcement that goes beyond 1 nanometer. That's practically the realm of atoms.
It is, and it has the potential to completely shake up the semiconductor industry. And, maybe even change how we rely on some of the manufacturing processes we use now.
This isn't just an incremental step, is it?
No, no, it feels like a massive leap.
Especially when you think about where we started.
Oh, yeah, the first chips back in 1987, they're around 3 micrometers. That's 3,000 nanometers.
3,000. So we've basically shrunk things down by, what, like 99.99%?
Pretty much. And now they're ramping up 1.6 nanometer production. It's incredible.
Okay, so for those of us who don't live and breathe electrical engineering, can you break down what a transistor is, in simple terms?
Sure, think of it as a tiny switch, an electronic switch that controls the flow of electricity.
Okay.
A good analogy is a water pipe with a valve.
Okay, I can picture that.
So the water flowing through the pipe is like the electric current. And the valve, that's our transistor. When you open or close the valves, you control if the water flows through.
Got it.
Same with the transistor. It has 3 main parts. The source, that's where the current comes in, the drain, where it goes out, and the gate, which acts like that valve.
The gate controls the flow.
Exactly. When you apply a voltage to the gate, it creates an electric field that either allows or blocks the current between the source and drain.
Okay, so that's how the basic switching happens. Now, I know that for decades, the go-to transistor was the planar type. What prompted a change from that design?
Well, the planar transistor served us well for a long time, almost 50 years. It was pretty simple to manufacture, and it worked. But we always want smaller and faster, right?
Of course.
And around the 22 nanometer process, we hit a wall. The gate length, the part controlled by the voltage, got so incredibly small that electrons started behaving, well, weirdly.
Weirdly how?
They started tunneling through even when the gate was supposed to be closed. Think of it like our water pipe. The valve is shut, but water's still leaking through.
Oh, I see. So you're losing control over the switch.
Exactly. We were losing control over the transistor switching ability. That was a major problem.
That's where FinFET comes in, right? It's not flat like the planar transistors anymore.
You got it. FinFET was a big shift. Instead of a flat gate, we moved to a 3-sided grip, which gave us much better control.
And I remember one of the major chip makers was the first to really adopt FinFET.
Yeah, they introduced it around 2012 at the 22 nanometer node. The leading manufacturer we're talking about today followed soon after, around 2013.
And now FinFET is pretty much everywhere, isn't it?
Oh yeah, if you look at any high-performance device, your smartphone, gaming PCs, they're all using FinFET technology.
Wow. So FinFET was a huge step forward. But like all technologies, it has its limits. Where do we go from here? I keep hearing about a 3D era of transistors.
That's the next frontier. FinFET was great, but we're pushing its limits. We need a new approach, something truly three-dimensional. And that's where gate-all-around GAA comes into play.
Gate all around, so even more control than FinFET.
Exactly. Instead of 3 sides, we completely surround the channel with the gate. No more leakage.
Okay, walk me through that. How do they actually build these GAA transistors?
So remember the fin in FinFET. In GAA, we take that fin and lay it flat, creating thin layers called nanosheets.
Nanosheets.
Yeah. And then we stack these nanosheets vertically.
Like a stack of pancakes.
Kind of, yeah. And the key is the gate material completely encircles each nanosheet. It's a true gate-all-around structure.
So we're talking about even less leakage and even better control than FinFET. That's impressive. And when can we expect to see GAA transistors in our devices?
Well, the next generation of process technology, the N2 node, is expected to feature GAA. And some rumors suggest that the very first devices using this technology might be launched pretty soon, maybe even in the next generation of smartphones.
Wow, so this is really happening. Now, what about manufacturing? I know EUV lithography has been a big deal. Does that change with GAA?
EUV, or extreme ultraviolet lithography, has been absolutely essential. It's how they create those tiny, tiny features on chips.
Right, using high-energy photons.
Exactly. And it's still going to be important, but with GAA, the focus is shifting a bit.
How so?
Well, building those stacked nanosheets and then getting that perfect gate wrapping it requires incredible precision, like working at the atomic level.
Wow.
So techniques like atomic layer deposition, ALD, become crucial.
What does that involve?
It's like painting with individual atoms. You deposit incredibly thin, uniform layers of material, like the gate dielectric, even around complex 3D structures. And then there's epitaxial growth, which is used to create those perfect nanosheet channels.
So it's a whole new level of manufacturing complexity.
Oh, absolutely. And after you deposit the materials, you need to precisely remove the excess material between those channels. That's where lateral etching comes in.
And then even more deposition to ensure the gate fully surrounds each nanosheet.
You got it. It's an intricate dance of atomic level manipulation.
So we've gone from planar to FinFET now to GAA. But there's talk about something even further down the line, something called vertical transistors. What's the idea behind that?
Vertical transistors are the next frontier. While GAA is a horizontal 3D structure, the vertical approach takes things, well, vertical.
So instead of making transistors smaller, we stack them on top of each other.
Precisely. One of the leading concepts is called CFET, complementary FET transistor.
CFET. And how does that actually work?
So you take the two main types of transistors, PMOS and NMOS, and you stack them vertically. The PMOS goes on the bottom, the NMOS on top.
Pleasure. And that cuts down the footprint by how much?
Roughly in half compared to having them side by side. It's a way to keep cramming more transistors into a smaller space, which is essential for continuing Moore's law.
I see. So it's about density as much as size. Now, I know there are different names for this vertical transistor concept, but CFET seems to be the most common. What's the breakdown of how these PMOS and NMOS transistors work within this vertical stack?
In a CFET structure, the bottom transistor is usually the PNOS. It has a gate-all-around structure, just like in GAA.
Okay.
And when you apply a negative voltage to its gate, it creates a channel of what we call holes.
Holes, so not electrons.
Think of a hole as the absence of an electron. It acts like a positive charge carrier, allowing current to flow.
Okay, I think I'm following.
Then, the NMOS transistor, which sits right on top, also has a gate-all-around structure. When you apply a positive voltage to its gate, it creates a channel of electrons, enabling current flow.
So both transistors in a CFET are using those thin nanosheets we talked about earlier.
Exactly. Just a few nanometers thick, around 10 to 15 nanometers wide.
Incredible. Now, I came across the name Sue Liao in relation to this technology. Who is she and what's her role in all of this?
Sue Liao is a real pioneer in the field of advanced transistor development. She's a key figure at the leading manufacturer we're focusing on, leading the research on CFET.
And she has quite a background, right?
Oh yeah, she joined this company in 2021 after working at another major player in the industry. She was involved in developing process technologies down to the 4-nanometer node. Now she's spearheading the development of groundbreaking architectures like CFET and also exploring the integration of new materials.
And I read that she and her team actually built a working CFET device.
Yep, that's a major milestone. It was the first functional CFET device, demonstrating that this technology is not just theoretical.
That's amazing. But I imagine stacking transistors vertically creates a whole new set of challenges, especially when it comes to connecting everything.
You're absolutely right. The biggest hurdle with CFET is the complexity of the interconnects. You see, in traditional chip designs, the interconnects, the tiny wires that connect everything, run mostly horizontally.
Right, in layers.
But with vertical transistors, you need vertical interconnects as well, and that introduces a whole bunch of problems.
Like what?
Well, vertical interconnects can increase resistance, which slows things down. They also increase capacitance between the layers, which can cause signal distortion. All of this can lead to delays and higher power consumption.
So creating these vertical connections is a massive engineering challenge.
It is. You need more processing steps. The alignment between the layers has to be incredibly precise, and there's a higher chance of defects. It's likely that CFET will require backside power delivery, meaning the power comes from the back of the wafer. And we might even need backside signaling for the PMOS transistor, just to manage those vertical connections effectively.
And on top of all that, there's the issue of heat.
Oh yeah, heat is a huge challenge. Modern chips, especially high-performance GPUs, already generate a lot of heat. And with CFET, where you're packing even more components into a tiny space, thermal management becomes even more critical.
So CFET has a lot of potential, but it also comes with its own set of hurdles. When do we realistically expect to see this technology in mass production?
The current estimates suggest around 2030. If it works out, CFET could be the key to pushing transistor density even further, allowing us to go beyond 1 nanometer. It's a game changer, but there's a lot of work to do before it becomes a reality.
It's fascinating how the focus in semiconductor development is shifting. It used to be all about shrinking the components, but now it feels like there's a greater emphasis on new materials.
That's a great observation. Early on, it was all about making things smaller. But as we hit the limits of silicon, especially with those shrinking planar transistors, the industry started looking for alternative materials.
And that's because silicon starts behaving strangely at those tiny scales, right?
Right. The electron tunneling issue we talked about earlier, that's inherent to silicon. So researchers are now exploring two-dimensional materials, 2D materials, which have some interesting properties.
What kind of properties are we talking about?
Well, 2D materials are incredibly thin, just a few atoms thick, and they seem to be much better at resisting leakage and controlling current flow at those tiny scales.
So they could be the future of transistor channels.
Potentially, the leading manufacturer we've been talking about is heavily invested in 2D materials research.
What kind of materials are they looking at specifically?
They're focusing on a class of materials called TMDs, transition metal dichalcogenides. They have the potential to create incredibly thin and efficient transistors, but we're still in the early stages of research.
So what are the main obstacles to using these 2D materials in mass production?
The biggest challenge is manufacturing. Right now, most high-quality 2D materials are grown on sapphire wafers and then transferred to silicon.
And that's a problem.
That transfer process is not very efficient or scalable. The ideal solution would be to grow these materials directly on silicon, but that's a complex material science problem.
So a lot of research still needs to be done in that area.
Absolutely, it's a frontier of materials science. Now, we've talked about lithography, specifically EUV. Is its role changing with these new architectures and materials?
Yeah, I was wondering about that. For the past few years, it seems like EUV has been the main bottleneck, the thing holding back progress.
It's true. EUV was crucial for the recent technology nodes, especially for patterning the interconnects, the tiny wires that connect the transistors.
Right, because the interconnects also need to be incredibly small.
Exactly. In fact, the transistors were shrinking faster than we could shrink the interconnects. That's why EUV, with extremely short wavelengths, became so important.
But with new architectures like CFET and the adoption of backside power delivery, things are changing.
They are. See, traditionally, both the signal and power lines were on the top of the wafer, but backside power delivery moves the power lines to the bottom.
Oh, that makes sense. Get those bulky power lines out of the way.
Exactly. That frees up space on the top for the transistors and the more delicate signal interconnects. And it also means we need fewer layers of metal on top, which simplifies manufacturing.
And less reliance on EUV.
To some extent, yes, EUV will still be essential for patterning the transistors and the signal lines, but backside power delivery reduces the pressure to keep shrinking the interconnects at the same pace as the transistors.
So it's a combination of factors, new architectures, new materials, and new manufacturing techniques all coming together to push things forward.
Precisely. It's a fascinating time to be following this industry. And, all of this progress in semiconductors means we're generating more and more data.
Oh yeah, that's a whole other challenge, managing that data deluge.
It is. And that's where companies like Stonefly come in. They specialize in data storage and management solutions, and they've been doing it for over 2 decades.
Stonefly, I've heard that name.
They're a pioneer in sand technology, a real leader in the field. They understand the complexities of managing massive amounts of data, especially with all these advancements in chip technology.
So for anyone listening who's struggling with data management, you're saying they should check out Stonefly.
Absolutely. Visit their website, stonefly.com, or reach out to them directly at sales@stonefly.com. They have the experience and the expertise to help. Stonefly is actually a sponsor of this deep dive, so big thanks to them for supporting us.
It's great to have them on board. Now, let's switch gears for a moment. I've noticed that the leading manufacturer's stock price has been down lately. What's going on there?
Yeah, there's been a bit of a dip, about 15% over the past few months. Some of that is due to concerns about potential U.S. tariffs on imported chips.
Tariffs.
Yeah, there's talk of tariffs as high as 100%. And some people think this is a way to encourage the leading manufacturer to build more factories in the U.S.
I see. A way to incentivize domestic production. But despite these concerns, the demand for their chips seems to be as strong as ever.
Oh yeah, absolutely. Despite the stock dip, their revenue is still growing strongly, around 43% year over year. The world needs their chips.
And building those advanced chip factories is incredibly expensive.
Hugely expensive. It's become a major barrier to entry. Back in 2007, there were about 12 companies making chips at the 45-nanometer node. Now there are only 2 companies that can handle the most advanced 3-nanometer process, and even they are facing challenges.
So it's a very exclusive club, and this leading manufacturer is doubling down on their commitment to manufacturing, particularly in the U.S., right?
That's right. They recently announced a massive investment plan, something like $100 billion, to expand their U.S. operations.
Wow, that's a big number.
It is. They're building 3 more advanced fabs, 2 packaging facilities, and an R&D lab, all in the U.S. Their existing facilities in Arizona are already enormous, supposedly covering an area equal to 650 football fields.
That's a lot of football fields. So with all of this investment and these advancements in technology, what's the outlook for chip prices?
The general consensus is that prices will likely continue to rise. The new architectures, the advanced materials, the complex manufacturing processes, it all adds up.
Plus the potential tariffs.
Right. But the performance and efficiency gains these new chips often justify the higher cost. It's an investment in the future, really. And as these chips become more powerful, managing the data they generate becomes even more critical, which is where companies like Stonefly, with their expertise in data storage solutions, play a crucial role.
It's true, we can't just focus on building better chips. We also need to think about how we manage the massive amounts of data they produce. Now, stepping back a bit, this whole journey in semiconductor technology is pretty awe-inspiring. It makes me think of that Stephen Hawking quote, "We are standing on the threshold of a brave new world."
I love that quote, and it feels incredibly fitting here. AI, high-performance computing, all of these fields are demanding more and more computational power. And that means more energy consumption. We're already pushing the limits of our power grids and cooling systems.
So power efficiency isn't just about saving money, it's becoming a fundamental requirement for progress.
Exactly. And that's where these new transistor technologies come in. We need to find ways to make computation more efficient, or we'll hit a wall.
And it's not just about the transistors themselves, right?
No, it's a multifaceted challenge. We need new materials, new architectures like GAA and CFET, better cooling techniques, backside power delivery, even new approaches like chiplets and photonic interconnects. It all has to work together.
It's a complex puzzle. So as we wrap up this deep dive, what's your final thought for our listeners?
I think the key takeaway is this. We're making incredible strides in semiconductor technology, but it's not just about faster phones and computers. It's about what those advancements enable, what unforeseen applications will emerge, what societal shifts will occur. We're talking about manipulating matter at the atomic level. The possibilities are truly mind-boggling. And as we enter this brave new world, companies like Stonefly, with their expertise in managing the data that underpins this revelation, will be more important than ever.
That's a great point. We need to think about the broader impact of these technologies, not just the technical specs. Thank you for taking this deep dive with us. It's been an amazing journey.
My pleasure.
And for our listeners, if you're interested in learning more about specific topics like backside power delivery or photonic chips, check out our other deep dives. We have a whole library of fascinating content. And if you'd like to continue this conversation, connect with us on your favorite professional networking platform. Thanks again for joining us, and a special thanks to Stonefly, a leader in data storage solutions for over 2 decades, for sponsoring this episode.